Um, and starting today, and I guess for the rest of the semester, we're going to talk a little bit more abstractly about things with the general goal of talking about the limitations of Turing machines and more generally about like real life computers and how they relate to all of this stuff that we've talked about for the semester. In my opinion, this is super interesting stuff, and actually, I think I alluded to the fact that actually there are things about Turing machines that make me think like deep thoughts about life in general and my relationship to God and the universe and other people. And so I hope that, I mean, you don't have to go down the rabbit hole if you don't want to, but I hope that you'll find this stuff really, really interesting and deep in ways that typical like math content is not usually that deep, in my opinion. I mean, in terms of like my own real human existence, math is very deep in other ways. But anyway, we're not going to talk about God and your place in the universe today, but this is sort of where we're going for the last 2 weeks of the class, and I hope you will come on the journey with me. Anyway, what I want to talk about just to get started on the journey is what kinds of languages are accepted by Turing machines. This is a major question that we haven't really talked about in detail. So, as usual, for a Turing machine, let's say M, we're going to write L of M for the language accepted by the Turing machine. The language accepted by M. And this is, the definition of that is, as usual, all the strings which are accepted by the Turing machine. So this is all strings accepted by M. And remember, what that means is just that a string is accepted when the Turing machine, you begin the Turing machine with this string on the tape, and somehow the machine ends up going into an accepting state at some point. Then everything just stops and the string is accepted, all right? So that we write as L of M. This is the same way we always say this. And there's a name for the category of languages that are accepted by Turing machines, just like, a language accepted by an NFA or DFA is called a regular language, and a language accepted by a stack machine is a context-free language. The name for this is a little weird, but any language accepted by a Turing machine is called recursively enumerable. Recursively enumerable. And we're going to write RE for that. Those words come from, it's a little unfortunate in my opinion, because that doesn't really sound like anything in terms of Turing machines as we usually discuss them. But this terminology comes from the somewhat tangled early history of this kind of foundations of computer science that was done. I mentioned this at some point, that Turing had all of these ideas about, what we now call Turing machines. And this was done sort of at the same time as another guy named Alonzo Church, who came up with equivalent ideas that look totally different, and he used different language for everything. And for the most part, Turing's ideas are the ones that kind of won out, even though Church's ideas were equivalent but stated in completely different language. This bit of terminology, though, comes from Church's approach. So Church called these things recursively enumerable languages, and that's what we call them, even though those are weird words. Because Church's basic idea was, rather than talk about a very simple kind of machine that can do certain things, Church just defined a very basic sort of set of very simple functions. And then by plugging these functions into one another recursively over and over again, you can generate languages. And so that's where this language, recursively enumerable, means. It means that these are languages which can be generated by recursive applications of the primitive lambda functions, which I don't want to talk about. We would talk about it if we had more time. It's very interesting, but we don't have that much time in the semester. Anyway, something that is interesting about Turing machines, different from the other types of machines that we have talked about, is actually there are two types of non-accepted strings. And this is an important distinction that doesn't exist for NFAs or stack machines. Sometimes the machine just gets stuck, like you're in a state and there's no arrow for the next letter that you see on the tape. So those words are called rejected, or those strings are called rejected. So a string is called rejected if the Turing machine just sort of stops. That's because there's no appropriate arrow in a non-accepting state. This is sort of what, at least on all of our examples, this is what usually happens for a string that's not accepted. It's not accepted because the Turing machine stops, and it stops because there's no appropriate arrow from one of your states. It's like if you're looking at an A on the tape, but the only arrow in the diagram has a B for the read, then you stop and the string is rejected. All right. A string is rejected if the Turing machine stops in a non-accepting state. Can anyone say though there's actually another way that a string can fail to be accepted on a Turing machine? Remember, accepted means it goes into an accepting state. So it could go into an accepting state, or it could stop in a different state. Or is there another alternative? There actually is another alternative. Yeah. Yeah, it could actually, a Turing machine can do some kind of infinite loop. That's not possible on an NFA, because on an NFA, every time you go across an arrow, you read a new letter, and you can't read letters forever from a string. But a Turing machine can move back and forth on the tape, and that means that it is possible that it could just go back and forth forever. So. And it's not hard to create an example that does that if you're trying to. So that is, I will just say, some strings. Those actually are not called rejected. They're not accepted, certainly. But they are strings for which the machine makes an infinite loop. So some strings result in an infinite loop. These are also not accepted, but we don't call them technically rejected either. So here's an example of a Turing machine. I just made up this machine specifically so that it would have an infinite loop for certain inputs. This one doesn't always loop forever, but for certain ones it does. All right, I gave names to my states here just so we can talk about them. So this is the starting state here. 1, 2, and my accepting state. All right, can we just try some different inputs and see what will happen? For example, what about the string AB? All right, I'm going to write out a little derivation here. So I hope you remember how to do these derivations. If I begin, we begin in state 1, and if I see AB on the tape, my first sort of starting configuration would be 1, pointing at the A, and then B afterwards. And then, so what happens on my diagram, if I'm in state 1 and I see A, I keep it as an A and move to the right and switch over to state 2. So this becomes A to B, like that. I move the state 1 position to the right. I move the head 1 position to the right, change it into state 2, leave the A like it is. And now in state 2, it says BBL. That means keep this B like it is and move back to the left and switch back to state 1 again. And so now it says 1AB. And I think you can see where this is going. That will just happen. It will continue going back and forth from state 1 to state 2 forever. And it doesn't change anything on the tape, etc. So this one loops forever if it's AB. In fact, would you believe me if I said actually any string which has A first and then B will work this way? It will loop forever because the head will never even look at the rest of the string after that. If there was more stuff after the AB, it will still loop forever. All right, so this one loops forever on any string that looks like ABX, right? AB followed by any more stuff. That will be an infinite loop for this Turing machine. Could we talk about other types of strings? So if it starts with AB, then it's going to loop forever. What if it starts with AA? Let's just try, 1AA. What does that do? This becomes, so it reads the A first and goes over here. It'll look like A to A, right? The one moves, the head moves to the right by one position, change state 2, leaves A like it is. And now in state 2, read A. What happens then? There is no arrow, which means this string is rejected. All right, so this is stuck, which means the string is rejected. And for similar reasons, actually any string which starts with A, then A, will be rejected. Even if there was more stuff after that, it doesn't matter, because the head will never get to that stuff. It gets stuck at the second A. So this, I'm trying to add on here, this rejects any string like AAX, right? So if it starts with AB, it loops forever. If it starts with AA, it's rejected. What are my other choices? I'm just trying to talk about like every possible string here. If it starts with a B, actually I think you can tell from the diagram, obviously. If it starts with a B, it will immediately be accepted, and it could have any other stuff. So this one loops forever on anything starting with AB, rejects anything starting with AA, and this one accepts any string starting with B, right? Anything like BX, could be BA or BB or anything starting with a B will be immediately accepted, all right? So in this case, this example is simple enough that we can just say straight up what all the behavior on all possible strings are. So there's a standard notation for this. So there are the accepted strings, and we write those as L of M. And in this example, the accepted strings are BX, where X is anything on AB star. All right, that's the language which is accepted. There's also the language which is rejected, and that we write with a R. And this, as I said before, would be AAX, where X is in AB star. Actually, technically speaking, the empty string is also rejected, because if you start and you see a blank, then it's rejected. All right. And then the other category would be the strings for which the machine loops forever. And those our book writes with a F, which I imagine means forever. I don't know. I would have used L, but L is already used. These are the ones which loop forever. And this one we decided was any string beginning with AB. All right. These are the strings which loop forever. Actually, I think there's one string. What about just A by itself? Doesn't fall in any of those categories. Is A by itself accepted or rejected or loop forever? I think that's rejected. If it's A by itself, you go here and then you see a blank and you get stuck in that position. So I should have put A is in this category also. I'll just add it on here. That's a technical detail that doesn't really matter. All right. Real life computing machines, like computers, they work this way too. They have some, when you are interacting with a computer, sometimes it loops forever. It's not supposed to do that, but it does happen sometimes, and you have to turn it off and turn it back on again. That's all. That's your only recourse at that point. If the machine somehow gets into an infinite loop, if you're lucky, it'll be like if you write a Python program that makes an infinite loop. There's a button you can hit to say stop doing that. But sometimes, like the computer operating system has an infinite loop, and there's nothing you can do but turn it off and turn it back on again. It's unfortunate, but that's how a real life computer is. All right. Anyway, in the first two cases, the either accepted or rejected. So in these cases, we say the Turing machine halts, And in the other case, we say it does not halt. So halting is a big thing that we're going to talk a lot about over the next few days. All right? And it's so important that there is another category of Turing machines. So here's a new definition here. If M is a Turing machine with F of M is the empty set, there's a name for that. So F of M, remember, is the set of strings for which the machine loops forever. So if I say that's the empty set, that means that this machine can never make an infinite loop for any input. That would be nice if our real-life computers worked that way. That's sort of how they're supposed to work, a real-life computer. Anyway, if a Turing machine has no strings for which it loops forever, then we say M is called a total Turing machine. All right? This is also, in my opinion, a weird word to use for this concept, but total Turing machine means the Turing machine never makes infinite loops. No matter what string you give it, it either accepts or rejects. That's it. It never makes an infinite loop. All right, that's called a total Turing machine. And there's a word for the languages that are generated by total Turing machines. So any language accepted by a total Turing machine is called, this is another confusing bit of terminology, recursive. All right. It's hard to keep it straight. Unfortunately, you just have to remember recursive means it can be accepted by a Turing machine with no infinite loops, whereas recursively enumerable is something else. That means it can be accepted by any Turing machine, but it might be a Turing machine which sometimes has an infinite loop. All right. Okay, so I want to talk a little bit about what sort of your feeling for these various categories means. You know, what we have now is, if I were to draw this little diagram of languages, we have the simplest ones are regular. All right. We have the next biggest category would be the context-free languages. And then we have these two new categories. There's recursive and recursively enumerable. So recursive means it is the language accepted by a Turing machine with no infinite loops. Recursively enumerable means it's the language of a Turing machine, just any Turing machine. So RE is bigger than just recursive because recursive has some restrictions on what kinds of Turing machines there are. You guys all right over there? It's a little distracting. So the next category here is called recursive. All right, that is languages which are accepted by a Turing machine with no loops. That is a Turing machine that can never enter an infinite loop. All right. And then the next biggest category is this RE category, recursively enumerable. This would mean, I guess, languages which are accepted by a Turing machine, but those Turing machines sometimes have infinite loops. All right, that's what the RE category means. This is accepted by TM, but that same Turing machine may have infinite loops on other strings. So the ones that are accepted, they don't make infinite loops, but those Turing machines might enter infinite loops on other strings. This is weird, and it may be a natural question to ask, is there any meaningful distinction? What's the point of being so picky about the difference between recursive and recursively enumerable? The answer is yes, actually there is a very big meaningful distinction between those two categories. And it has a lot to do with how computers work in the real world. So I would like to just say a few words about these two categories, recursive versus recursively enumerable. So the way that I think about these is a language is recursively enumerable. What that means, I already said this, but I'm just going to remind us. This means there exists a Turing machine with, L is the language of that machine. But sometimes this Turing machine may have an infinite loop for some inputs. All right. Now you have to imagine, what if you are actually trying to use a machine like this in real life? The idea is you sort of give it a string, and then it does some stuff, and you wait until it either accepts or rejects. Now this one also sometimes will just go forever. All right. This means, in practical terms, practically speaking, it is hard to tell if a string is looping forever or if it is, I will just say or if it's taking a long time to be accepted. And you've probably gone through this, the struggle is real on these streets. If your computer is just sort of stuck, you go through a little debate in your mind. Is it really stuck forever now, or do I just need to wait a little bit more? All right. So practically speaking, it's hard to tell if a string is looping forever or if it's just taking a long time to be accepted or rejected, whatever. All right. I've lately been playing a cheap video game called Vampire Survivors. Anybody into this one? It's good. It's very cheap, and but it's every time you finish like one level on my computer, it just totally freezes for about 30 seconds, and then everything's fine. And the first time this happened, I thought it had crashed, but it didn't. This is the struggle that I'm talking about. So a Turing machine like this, if it's possible that there are infinite loops, what it means is, practically speaking, you can't really use this in a nice way to give you answers to like yes or no questions, accepted or rejected, because you don't know if it's going to be running forever or if it's just going to be running for a very long time before giving you the answer. All right. So practically, it's hard to tell if a string is looping forever or if it's just taking a long time to be accepted. So what I would say is, in this category of languages here, or in this sort of hierarchy, the ones which represent truly useful computing machines are this one. All right. This one right here are sort of truly practical for computing answers to important questions. Now, for a Turing machine in this setting, it's just like yes or no questions, accepted or rejected. So those ones, the recursive ones, are truly practical for computing answers to yes or no questions. Whereas these ones here, I would say, they can sometimes give you an answer, and if it gives you an answer, then that's a clear answer, accepted or rejected. But sometimes they will loop forever, and in that situation, actually, you don't know if it's looping forever or if it's just taking a long time to give you your answer. So these ones, I would say, these sometimes give good answers, because if it actually stops and gives you an answer, then that's great. But sometimes not. That is to say, sometimes they're going to make an infinite loop, and it's really not possible to know if that's really an infinite loop or not, or if you just have to keep on waiting. All right. So when it comes to like computing machines that we want to use in real life, really we want this category here. Those are ones which never have infinite loops in them. Although, as you all know, and as I've already said a few times, real-life computers that we use are not like that. Real-life computers that we use are really more appropriately described in this category, because the computers that we use, actually, they do have the possibility of infinite loops. Now, usually we try to avoid that. It's almost never useful for your computer to do an infinite loop, but that's the computers that we use are actually more like in this category over here. All right, that's so this is sort of the big difference between RE and recursive. So I will just say, to finish this little sort of discussion here, RE means sometimes this Turing machine may have an infinite loop for certain inputs, versus L is recursive. This is sort of better from a user's point of view. L is recursive, means that the Turing machine will always halt and so practically speaking, this makes it much better. So this means we can always just wait for the answer. It might take a long time, but you never have to worry about, maybe I just should turn it off because maybe I'm not getting anywhere. Actually, it is always getting somewhere. You might have to wait a long time, but you can always just wait for the answer. All right? This is the big difference between recursive and recursively enumerable. All right? There is an important distinction in terms of, and this is important for, real-world machines also. All right? Great. That was just a little kind of a taste of this sort of universe here. Actually, we are going to talk about certain example languages which are in this category, and also in this category, and also out here that are not part of any of this business. That is languages which they can't be accepted even by a Turing machine, which sometimes makes infinite loops. But before we get to that, I thought maybe we should start talking about real-life computers a little bit. And I've been trying to make analogies about practically if you were using one of these machines as if it was a real thing. Now, you can sort of build a real-life kind of Turing machine. I've seen them built out of like Raspberry Pis and such. With actually, people have made things with like an actual physical tape and a little marker that writes on it. They're kind of silly, but kind of cute. Of course, nobody uses an actual Turing machine in real life, but the point is that a Turing machine is meant to be like a real-life usable computer. I would like to talk about some Turing machine variations. The Turing machine, all it can do is read and write on the tape, and then accept the string when it gets to an accepting state. But we could think about, can we sort of add functionality to make a Turing machine, I will say, stronger? That is to say, make it able to compute more languages than it could before. Can we add features to make a Turing machine stronger? One very, I'm going to try and think about all the natural things you might think to make a Turing machine even better than it was before. One simple variation could be, how about 2 tapes? Can you imagine it? A Turing machine which has 2 tapes, so that in each step it can write something on one tape, but it could also write something on the other tape. You could imagine a machine which maybe uses one tape just to read the inputs, and then uses the other tape, like a completely blank tape, to store memory or whatever. This seems like this could be more useful. What if we had 2 tapes? The question I want to ask is that thing with 2 tapes actually better than a Turing machine with 1 tape? Are there things that the 2-tape machine can do that are impossible to do on the 1-tape machine? So I imagine, something like 1 tape which begins with the input string, A, B, A, whatever, and then maybe blanks forever. And then it just has another tape here, which is, I suppose, starts off with all blanks. And this other one you can just kind of use as your scratch paper as you're going along. as a practical instrument, it sounds like that could be useful. But is that actually more capable than an ordinary Turing machine which has only one tape? I would say I don't think that that actually is more capable, because I would say something like the ordinary Turing machine already has blanks going forever here. Whatever kind of scratch work you want to do down here, you could also just move the head way over to the right and put stuff over there too, and then move it all the way back. It would be a pain to work with, and it would be more convenient to have the two tapes, but actually there's not much of a difference. So here, the two tapes may be convenient, I would say. Convenient. But they don't actually allow for more languages to be computed. Right? In fact, it's not so hard to think about. You could, if you had one of these two-tape machines, actually, any two-tape machine can be simulated. This is kind of a big concept that Turing talked about, by a one-tape machine. I mean, Turing talked about just the concept of simulating one machine with another was kind of a big deep thought in Turing's mind. Any two-tape machine can be simulated by a one-tape machine. Check it out. If I have a machine with only one tape, I can still write things on the tape that look like this: A comma blank, B comma blank, A comma blank, blank comma blank. What I did is I just took the two tapes that I wrote up there and I just wrote them together as pairs on the one tape. And now the Turing machine, whatever you thought you could do with the two tapes, you can do the same thing here, treating it as if this is a one tape, but I'm using alphabet symbols on the one tape which treat it as if there were two things in each spot. All right? So now this is a one tape machine where now the alphabet here for this machine now consists of pairs of things, but it's still a one tape Turing machine. So any two tape machine can be simulated by a one tape machine. And so what that means is that allowing for two tapes doesn't actually make a stronger machine. Right? This is not only true for two tapes, really any number of tapes. If you want to make a Turing machine with 5 tapes, that's basically the same as a Turing machine with one tape. And I want to write that as a theorem. We're not going to do the proof of this. But just to say very specifically what I mean by this, let's say an N-tape Turing machine can be simulated by a Turing machine. I mean like an ordinary one-tape Turing machine. So any N-tape Turing machine can be simulated by a Turing machine. What I mean by that specifically, i.e. if, let's say, M sub n is an N-tape machine, then there exists a ordinary Turing machine, M, with the language of M is the same as the language of Mn. The rejected set for M is the same as the rejected set, and also the looping set is the same as the looping set. All right? If you have a tape machine which uses N tapes, then that same thing, whatever that machine is doing, can be done on an ordinary one-tape Turing machine. All right? So if you're ever talking to your friends about how awesome Turing machines are, and you're like, yeah, it has a tape, and your friend is like, what? That's stupid. Why doesn't it have 10 tapes? You say, well, whatever you can do with 10 tapes, you can do with one tape. So you might as well, if you're talking abstractly, you might as well just focus on the one tape thing, because it doesn't do you any good to add on more tapes. All right? Any more variations that you can think of? How about, here's another variation. We said that every step the machine has to move to the right or move to the left. Wouldn't it be awesome if the machine could stay put sometimes? Huh? Would that make a better Turing machine if instead of making it so that it has to move to the right or it has to move to the left, how about a Turing machine that is allowed to stay still in one step? Could you imagine simulating such a machine by using an ordinary Turing machine? Can anybody say, like, what if I have a machine which is allowed to just stay put in one step? Is that somehow equivalent to doing something else on another one? Yeah.
Just be going right and not changing, then going back left and not changing anything?
Yeah, right. So if I have a machine which is allowed to stay put in one step, you can convert that to a normal Turing machine by just like every time I have, like on my diagram, every time I have an arrow that stays put, you convert that into just move to the right one spot and then move back to the left one spot. It doesn't matter, allowing the machine to stay put. Similarly, for any kind of, what if I allow the machine to move 2 spots at a time? That also could be converted back into a machine which moves only 1 step at a time. So I'm going to say any, so also any kind of head movement with jumps of several spots, several locations. Also, any head movement with jumps of several locations is equivalent to an ordinary Turing machine. All right? The fact that the head is only allowed to move 1 spot at a time really is not a limitation. That's a simplification for the sake of talking about an abstraction. You might as well just assume that your abstract machine is operating in very simple terms. But it's not a limitation, theoretically speaking, because any fancier thing could be simulated by one which only moves 1 step at a time. All right. If you think about, so what is a real-life computer like? Basically, a real-life computer is a Turing machine which has something like millions of tapes, and also it can jump long distances sort of in the code or in the along the tape. The tape, you could say, of an ordinary computer, like the tape in my phone is some kind of, I guess there's several types of memory in the phone, but there's sort of RAM and there's also, I don't know what the memory is. Is it a flash card? Something like that in my phone. But anyway, I will say a real-life computer is basically a Turing machine with many tapes and I will just say a jumping head, right? This analogy was more obvious in the past when we had magnetic hard drives, which I think my computer has a magnetic hard drive in it, which was like an actual physical sort of circle that had a real thing that they call the head. It was like on an arm, and the thing would spin like a record player, which was also a thing that we used to have. And the arm would go back and forth, and the arm, it spins to help the arm move from one location to another, and the arm can also go back and forth to move. That's what a Turing machine movable head is really like. So a real computer is basically a Turing machine with many tapes and a head that can move sort of far distances at a time. And you can think of the tapes of a real life computer. For instance, my laptop, you can plug, it has a keyboard. You could imagine the keyboard is analogous to another tape where the user can just fill in strings sort of on the fly as the machine is going. And you could even think of something like the mouse as another tape which sends movements that can be interpreted by the computer as it's running. And you could even think of things like the internet or your Wi-Fi as another tape. It's another source of input which at some point is converted into binary strings which the machine is processing. All of these ideas have basically, I will say it this way, any sort of, this is an important caveat that I'm putting in here, but any reasonable feature you can imagine you can imagine, if you imagine making the Turing machine a little more powerful by giving it some kind of new capabilities, any reasonable feature you can imagine will result in an equivalent type of machine. If you think of your Turing machine as having other sources of input, basically you're talking about other tapes or other kinds of fancier head movements. Those can all be simulated by a head which only moves one position at a time. All right. In this sense, the Turing machine, and this was Turing's big idea, was not that Turing didn't see like the future would be a world run by machines of little tapes. His idea for the tape was the Turing machine is a universal machine. That is to say, it's meant to be a very simplified sort of distillation of what is important about real-life computing machines. And in theory, any real-life computing machine could be simulated by one of these Turing machines with a single tape. All right. Real-life computers are not typically thought of in this way, so I will just say that people do think about, the Turing machine basically has the head on the tape, and that's it. But real computers have more complicated, some of you probably know about this, probably some of you I'm sure know more than I do about this. Real computers have more complicated what they call architectures. That is to say, they have more pieces to them, more than just the tape and the head, which has certain states. So the basic model which led to the computers that we have today, they're not really meant to be like Turing machines exactly, but the sort of, I will say, the standard model for basically all like commonly used computers today is called the von Neumann architecture. There were other designs, architecture, and the von Neumann architecture basically has an input device, which you could think of as like a tape that feeds into what they called the central processing unit, and then that's the CPU has its own sort of internal memory, and the CPU can store things in the memory, and it can also retrieve things from the memory, and then the CPU has some kind of an output device. This is the standard von Neumann architecture. And this is what our modern computers pretty much all have, this basic structure to them. A typical computer has many input devices, like my computer has a keyboard and a mouse. It also has the Wi-Fi. It also has like, my phone has like a tilt sensor in it and all kinds of other sensors that can work as input. And then the output is basically the screen, but also the computer has speakers, which, sound output. It also can use the Wi-Fi for output and so on. But this is the standard model of computers that are actually used in the real world. But I'm here to tell you this is equivalent. So a von Neumann machine is, from an abstract point of view, equivalent to a Turing machine. You probably like using von Neumann machines. You probably would not like using a Turing machine, but if you built one in real life. But a von Neumann machine is equivalent to a Turing machine. That's what I'm trying to say. And all von Neumann machines are basically interoperable. Now, they're not always meant to be interoperable in a nice way, but von Neumann machines can simulate one another. Machines can simulate each other. Like, what I mean by that is you can, you can run sort of SNES on Windows, right? Like that, there's an emulator that will let you play Super Nintendo games on your Windows. You can even emulate Windows on a Mac. You can emulate Windows on Windows. Like that sounds silly, but actually there are good reasons to do that. You can run a simulation of another computer inside of another computer. So, Mac on Windows, Linux on Linux. People do this often actually. If you want to create if you're developing operating systems or developing servers, you want to, rather than running it on two separate computers, you might as well run sort of both computers on the same computer. It's useful to do those sorts of things. All right. This kind of business, Turing thought a lot about this kind of simulations, and this is what this is related to one of the most famous kind of ideas from Turing is what we call the Turing test, which Turing had this idea about artificial intelligence. Turing thought of before most people thought that it would ever be possible to make like a thinking machine, and they asked Turing sort of Turing thought about how would you even know if a machine is a real intelligent thinking machine versus a machine which is just trying to fool you into thinking that it's intelligent. Actually, people are now talking about all these things a lot lately. I'm sure you know that AI has been there have been major advances in the past few years. But Turing's basic idea is something he called the Turing test. He said the way that you can know if a machine is truly intelligent is by interacting with it, asking it questions and so on. And if you can talk to it and you can't tell that it's a machine, then that means it's intelligent. So I think this is referred to as the Turing test. And I think by Turing's test, for instance, like ChatGPT is a real intelligent being, according to Turing's test, which is a little unsatisfying to me. But, who am I to argue with Alan Turing? Some people have made a lot about this idea of Turing and his fascination with simulations. He actually talked about sort of a gender game about. I don't know much about Turing and his writings, but he talked about people like a man acting like a woman or a woman acting like a man. And you can think about a similar idea, like if a man can act like a woman and everybody thinks that they're a woman, maybe that means they really are a woman, just like if a machine acts like it's a thinking machine and everybody thinks that it's thinking. I think Turing had a lot of sort of gender ideas, which I would say are very modern in the way that it plays out from a modern point of view. Turing was also gay, and it had a big. It's sort of his sexuality kind of led to the end of his life. He was basically arrested for being gay, and then he was put on some kind of gay cure hormone therapy, which totally made him like very mentally ill, and apparently killed himself after this whole situation started. So I think there are a lot of people who now see this kind of Turing's fascination with simulation as some kind of like indicator of the deep dark soul that he had and his horrible situation of being a prisoner of his gender and sexuality or whatever. I actually don't know if that's, to me that seems a little overblown from a modern point of view, but maybe that's all related. Anyway, we're going to talk about some more details about this business about simulations next time.